So seeded extractor. So as you remember, or maybe not, hopefully you remember, there is no one function that does it all. There is no one function that for every k source x, right? So that's a random variable with mean entropy k. You shouldn't worry too much about the definitions, but it has k bits of entropy. The guarantee should be, I mean, it doesn't exist. There is no one function that outputs up to epsilon error m random bits, even if m is 1, and even if k is like n minus 1, unless, of course, epsilon is like 1 or something. It's trivial, just do anything, fine. And that's why one of the branches of this field was, said, well, usually we have some randomness. Either, I mean, usually, actually, you don't have the randomness and you kind of iterate, or you do something, we'll see. But let's kind of imagine we have some randomness here. And you should think of this as very small. So that's a seeded extractor. The goal about seeded extractors is, you can phrase it in several ways, but let's fix one. So let's say you are given, obviously you are given n, right? You know how many bits you are going to get. And you are given the error that someone asks you to have at the end. And you're also given k. So someone tells you, or at least a low bound of k. Someone tells you have that many bits, don't worry about it. That's what I'm shooting for. And your goal is to minimize, like to construct efficient extractor, which minimizes the seed. That's called the seed length. I mean, this is the seed length. This is the seed. And maximize what? M. And you want to output as many bits as possible using a few random bits as possible. And you can kind of reverse it. You can say maybe you are given M and you want and so forth. But let's fix that. And how should you know what to expect? Like, should you try for 30 years to construct an extractor, or should you do something else? Probabilistic method, exactly. Right? You just run the probabilistic method. It's not trivial here because like you have like Aleph k sources or something. But you can show that any k source is essentially, or it is a convex combination of what's called flat sources. And a flat source is just, so a flat source, I'm not going to do that, but just, it's just x is uniform. So x is a flat source if it's uniform over a set of size 2 to the k, or size whatever, but if its entropy is k, it's like 2 to the k. So the histogram looks like that. It's flat. That's why it's called a flat source. That's the set, that's the support, and everything here is 2 to the minus k. And if you can easily show that if you have a function that works on certain kind of sources, then it also works on convex combination of those. So really, it's enough to consider flat sources, and from there, it's an easy exercise. I can just show you, but it's an easy exercise to prove the existence of. We'll do it for 2 sources anyhow. So let me choose one of them. For seeded extractors, where D, what's your guess? How many random bits do you need? And let's start with this. That's actually, I think, more intuitive. M is right, k. Because you have k bits of entropy, you expect that. You also can like output the C. Like you have also D random bits there. And I mean that's too good to be true, actually. There's always what we like to call a heat loss, and the heat loss is always 2 log 1 over epsilon. It's always for the same reason. This 2 is in the 2 in the exponent of Chernow, epsilon squared. Just standard deviation stuff. It always happens. It's optimal. That's what you can do. And minus a constant, right? I mean, who cares? So everything is like 1, 1, 2, right? So and that's a constant. The reason that that's a constant is because the base here is 2 and not lan or something, but never mind. And also the constant in Chernow, anyhow. And D, so this is, can you kind of figure out, maybe, but if I don't remember, I don't expect it.
You have like the 1 over alpha,
no, that's the merger. Oh, I see. That's an extractor, not the merger.
maybe the 1 over even bigger.
Right, so you definitely have actually 2 log 1 over epsilon. Never mind the 2 really, but there's always, you know, on the safe side, you always do that because that's actually the expression. And in terms of n, what do you think? Log what? Log KD. But if you have less than log n bits, I'm slightly cheating here. If you have less than log n bits, you don't have like enough randomness to access an index. So you might miss randomness, right? So you need like, so you definitely need not log n really, but log n minus k, because that's the kind of entropy deficiency that you have. So think you have like, maybe you have, that's a special case, you have n minus k, so you have your k random bits and n minus k that are not. You want to have enough kind of randomness here to access all the bits in a sense. Right, so that's what you should do. I mean, that's a probabilistic method and it's optimal up to this constant. What do we know? So we don't know that, obviously, that's like, we never know that. I mean, except for this when we know better, but and also that, I guess. But right. But for the proof, like I'm doing that for the analysis, and I kind of looking at the distribution of the whole functions like that. But at the end of the day, I'm concluding that there is one function that works. Right. So that's existential. And what do we know? So we know essentially like, so we know it's something like that. If you are very similar to what happened for the mergers, and for kind of the same reason, if you have seed length, I mean, we know several stuff, but generally, if we have with seed length like that, so alpha is a parameter, you can output 1 minus alpha k bits of entropy. No, that's for the merger. So that's you can do slightly better. You can actually have k over log k or something, but essentially that's what we k like k minus k over log. So if you think of alpha as constant, then we know how to output any fraction of the entropy, any constant fraction with logarithmic seed length. So you're definitely not insisting on the minus k here because you definitely have that anyhow. So that, and what we want to have is this thing. I think it's cool. It's very good. In this? In D. No, you need more random bits, right? Rather than 2 or like minus. Yeah. So actually, you know what? I mean, that's fine, but yeah, maybe you can get rid of that here because it kind of appears 0 or something. But let me stay on the safe side. So how do you construct these things? I mean, I'm not going to actually like tell you everything, but just there are like 2 ways of doing that. I'm just going to tell you one of them. Actually, the one without the mergers. The one with the mergers is slightly more complicated, but it's always kind of the same thing. What you do is you start with your k source, and it has n bits. And what you do is you compress it, like, or condense it. So you apply a function using a little bit of seed, essentially the seed length that you get at the end. It's not really a little bit, it's the same. And then you get something which is like, maybe 1 plus alpha. So it's still a k source, you lose nothing in terms of entropy, but now the length is like 1 plus alpha times k. So it's compressed, the entropy is condensed. An extractor is where this is 0. Right? You have k bits of entropy, like up to plus minus epsilon of error. You have k bits of entropy. Here you have this gap. It's like, you should think of it as like condense it. And here you have a problem which is significantly easier, turns out, because the entropy is so high compared to the length that and now you can use like essentially basic, like it's not basic, but basic techniques. It's like 3 hours. In 3 hours, I can do that. Okay? I can show you that. It took 3 years, but to show you that it's 3 hours. And the condenser, that thing, I think someone presents something. Yeah, right, good. So the condenser, so there was this one paper by Guruswamy, Umans, and Vadan, GUV, which they constructed this condenser and immediately improved like 20 papers on extractors in one shot. Each kind of was devoted to something else, and they just that's that's going to work. Interestingly, it came after a breakthrough in coding theory, but but Amnon and his student, I think Itai Kalev, had this really beautiful alternative to that construction, which hopefully can also be improved. I mean, that's kind of probably stuck. So, right, so if you want, you can come and see that the presentations. But actually, it's earlier, we'll talk. Right. So therefore, the entropy is more accessible, right? So you think of K as like log n. Here you have log n random bits in a sense hidden within n bits, and here you have log n random bits. Again, it's not like random bits, but bits of entropy that are hidden within like maybe 2 log n or 1.1 log n. No more random. Why? So you have to invest less. Right. Yes, I'm not going to say anything more about seeded extractors. Maybe for mergers, I'll just tell you what's the point there. So the point about mergers is that, and they are used in so you first do that anyhow, but then you can use mergers also. The point about mergers is that it allows you to do kind of non-determinism. So in what sense? So say you have a source and you don't know like where the entropy hides in a sense. So you kind of maybe partition into blocks. And if you knew that here you have like more randomness than the average or something like that, you may kind of start work with that and then invest it back or something, but you don't know where the randomness is. So what you do is you consider all possible cases, and you'll get like maybe you have T blocks, you'll get T outputs, you put them in this thing and you merge them. No, because good, these are dependent outputs. Right, so you kind of guess that that's where the good block is in whatever sense good block means, and so maybe it's this one. Now the other blocks are you apply the same procedure to the other blocks, and this means that these are dependent now. So it's not a T source extractor. We'll talk about that. It's a merger, right? Exactly. It's a merger for. So if you have a merger for T inputs, what you do in the homework, by the way, then you can, with a little bit of extra seed, you can merge them. So it allows you to do like non-determinism. I don't know where it is, but don't worry about that. I'm going to try all of them. The fewer, the better, the shorter the seed here and so forth, but I'm going to try all of them. So that's the point of a merger, really. And the point of a condenser, I think, is like really intuitive, like just making the problem easier. Okay, and the math that goes here and here is like really nice. I mean, you saw the merger. I think it's obvious that it's really nice. If you don't think it's nice, I can help you. And the condenser, it also uses the polynomial method, like the original paper, in a more sophisticated way than the merger. And the new paper does that even in a more sophisticated way. It's a really cool paper. You should definitely come to this talk. Okay. Any questions about seeded extractors? We spent like 5 minutes on it. And doing like extracting from here on, it's less kind of beautiful. It's less elegant. You do stuff. You hash it and you use expanders, and it's a chain of things that you have to do. Actually, it's actually. I mean, I must say it's somewhat ugly, but then if you think about it, it's exactly the zigzag for extractors rather than to expanders. It's kind of the same idea, and in the zigzag, it's beautiful. So I have a conflict with myself about how don't I like it when I do extractors and when I do graphs. So I don't know, but it is beautiful, I guess. But just yes.
If you do like a multi-level merge, will you benefit from something like?
Right. It take 2 at a time or something. Or
like instead of T, you take like 2T or 3T or something, and then you do the merging for each one, and then you merge.
No, actually you lose. Good. So for example, in the homework, no, in the lecture we gave a merger for 2 variables with this seed length. So you immediately, essentially, you need to look up at the errors, but you immediately get a seed length like that, because you can do it like in pairs and then in so forth. There is an issue with the error, so maybe, and never mind. And what you're asked to do in your homework is just that. So it's actually harder, right? So there is a better way than doing them like 2 at a time. Kind of surprising, but it's the same proof, really. If you understood the proof, it's the same thing, essentially.
This case, you assume that one of them, only one of
them. Right. If you assume more of them are uniform, then obviously it's easier, but it doesn't help you. But if you assume more of them are uniform and you want to output more stuff because it's fair, right? They're uniform and independent. You know, more stuff. That's a harder. I mean, we don't quite know how to do that. I think Zev is working on that. Maybe he did something, but which I'm not aware of in the last years. No, not really. Right. The thing you need to improve is this one over alpha. If you can get rid of it, that's perfect. If you can get it smaller, obviously good. If you can get an additive dependence rather than multiplicative, it's surprisingly strong, and so forth. But you need to know like the rest of the construction, like to know what you want from this thing.
And if you do split that to roots of the roots.
Yeah, so it's slightly better. But eventually, I mean, the best point is at the end. So you can like twos are the worst. T's at once is the best. I mean, because we know how to do it. It could have been the case that we wouldn't know. It could have been the case that the techniques used for merging two wouldn't kind of scale to merge T. And then what you're saying is essentially the best we can hope for without new ideas. But actually what I showed you is really, I mean, the thing is called the curve merger. You pass a curve over the points, and I passed a line just to kind of demonstrate it. So it's really the same thing, the same proof. It goes as is. So it, yeah. And even more, for example, if you know that no row is completely uniform, which happens in applications, but one row has a lot of entropy, then actually the same construction as is guarantees that the output will have the same fraction of entropy. Up to the alpha that you anyhow lose, you lose that from what you have. So it's a really robust construction. It kind of does, it's, it just, whatever you want, I'm just going to do it the same thing without moving. So there is another notion that's called a strong seeded extractor. I'm just going to say that in a second. I'm going to use that in a second. So the other notion of strong, I really don't like this name. Someone was lazy, like no one can understand what it means, right? Strong. I mean, it's also kind of reductive for the seeded extractor because they are strong. So what's a strong seeded extractor? So so what do you know? You know in a standard extractor that, let me write it like that. So if this is your source and this is your seed, you know that this random variable is close to uniform. A strong seeded extractor tells you that not only this is uniform, but actually for most y's, kind of similar to what happened in Nissan, for most y's, for most seeds, in maybe 1 minus epsilon fraction, something, this thing is uniform. So it's not that the randomness from y that does the job. Like it's like that most fixed choices of seed, for every given source, if sufficient entropy, most choices of the seed, even if I apply this deterministic function now, they will. Right. So it could be like that no little y is good, but somehow like when you steer them together, it makes it uniform. It's like right, like in numbers, it's like maybe you want to approximate 1/2, and you have like probability distribution, which is like half of the time -1, half the times 1. It's never quite that, but the average is good. So that's the analog of this. And here the analog is that actually, there are some outliers, but most of them are here, around 0. Like most, I don't know. Yeah, it seems like it's the same. That's a much stronger notion. and so, yes. Exactly. So the thing you can hope for, with the same seed length, but you can't hope to output D, because you don't use. I mean, what you assume here is that when you fix D, the D bits you're uniform. So you can't expect to benefit from these D bits. So and that's what you should hope for, right? And you can. I mean, the probabilistic method gives you that. Yes. So it turns out that most constructions that are seed extractors are also strong, and there is also a way to black box take a seed extractor and make it strong. We know a lot of stuff about these things. No, not with a logarithmic seed, because we don't know to do it in this case even. We do know how to do it if you give me log square n seed or something. That I can do, or even log n log k. But not log n. Log n would be would have like it would be amazing.
Like you assume you have an optimal.
Yes, it will give you optimal. Right. I think yes. Oh, good. So one example, I didn't meant to do that, but one example actually it came. So I told you the two source came before seeded, but actually this notion. Well, I'll give you a game here, and it turns out that hidden in it is a seeded extractor. So there was this following game actually it was initially about quantum computation, but you can ask it's also about the classic computation. You have two parties, Alice and Bob, and they have they want to agree that they want to do key agreement. So they want to agree on an n-bit string which is uniform. Unfortunately, life happened, and maybe the thing that they agreed on was uniform initially, but after some time, some adversary learned something about it, so now it's not longer uniform. So Alice and Bob, time takes its toll, and the n-bit string which was uniform initially, the thing that they agreed on, is now not uniform, but it's not like nothing. It has k bits of entropy. It has min entropy k now. So maybe stuff happened, an adversary learned stuff about this k, and at this point of time, the min entropy of x is k. Some k. Maybe n over 2, maybe. You lost some bits, but it's not like you don't want to throw it away. And there is always this Eve, right, that listens. Always. And the question is, how can they make it better now? And it sounds impossible initially, because everything they'll say, the adversary will hear. But the point is, it doesn't care. It's just saying, I'm going to sample y, suggestive notation for a seed, and I'm going to send it to Bob. And if you can hear that, I don't mind. You know why. And then we are going to replace x by, so the new x, maybe I'll put it here. So x new is going to be like that. And that's it. I mean, because the extractor is strong, even knowing y with high probability over y, this is uniform. And actually, any one-round protocol yields an extractor. It's just another way of saying what an extractor is. No. So she knew some things about x, which made the entropy of x smaller. Maybe it was uniform, and she learned the first n over 2 bits or something, or some bits. We don't know which bits. If you know which bits, then you just discard them. Right.
But then, the sign changes.
Yes, but it's fair, because you have only k bits of entropy. You cannot expect to make n bits of entropy. You just want to make it clean again. You lost some bits, so you can.
Yeah, I'm just wondering, how can you do the same thing you did to just
Right. So usually you should start you should plan ahead and have some n, and then the adversary will learn some of the bits. So you don't know which bits to use, but you learn that half of the bits will learn. So you're going to. You usually can bound how many. Usually it's the amount of communication that happened before. That's how many bits the adversary learns. So you have a good bound on k. You apply the extractor, and you don't get more bits. You get as much as bits. Depending on how many bits the extractor outputs, you get as that many bits minus this thing. Okay? In a picture, by the way, regardless of that, strong seed extractors, the way I like to draw it is as follows. So these are the seeds. It's really similar to the little discussion we have with hash functions. So there, for every program, most of the hash functions succeeded. And here what's going to happen is that for any source X, but for a small number of bad seeds, all of these seeds are good. But you don't know that. That depends. That's a said phase as a function of X, as the distribution of X. But you know, who cares? I mean, just, okay. So now I'm kind of playing in my head with two options: being dramatic or just telling you something. Okay. I'm going to be dramatic for a second. Okay.